So yesterday we have seen the color channel filtering and how the color should be perceived. Today we want to see the basic principles of filtering, okay, and the histogram of any image. Now, so now, there is one specific thing about the images that we should know is that yes, every pixel represents a color. In the grayscale, the color value will be between 0 to 255. In the color scale, the value will be 3 channels, one for red, one for green, one for blue. Now, an image quality is represented not only by the pixel values, but how a pixel is perceived in corresponds to its background. Okay. Now, see, say for instance, this is my image. Okay, and we have an object something like this, and so see, let us assume that this is our image. Okay, you can clearly see that the object is not quite easily visible. Okay, that's because its color is almost similar to the color of the background. This is known as the contrast. Contrast is also defined as the change in the brightness from one object to its background. Okay. In this case, the object is more prominent because there is a lot of change in the contrast. Okay, that means there is a lot of brightness change from one object to the other. Okay? So, in order to assess the quality of any image, it is very essential to know what is the brightness and contrast of the image, overall brightness and contrast of the image. If the contrast is very high, that means image is on the lower side, that is blackish, okay. And if brightness is very high, the image is very bright, okay, that is, it should be looking like sun, okay. So the contrast of an image is very high, you can increase the brightness a little bit for the image to be more visible. If the brightness is very high, you can reduce the brightness and increase the contrast in order to make the, improve the visibility. So, how do we basically measure the brightness and contrast in image? If we assume that the image is a grayscale image, it will be comprising of 0 to 255 color. So, number of times each color has appeared in the image will give an estimation of the brightness value of the image. So, suppose if we count totally how many number of times 0 color has appeared, how many number of times color 1 has appeared, 2 has appeared, up to that 255 has appeared. If the color between say 200 to 255 are appearing more number of times, then brightness is high. If the color between 0 to 50 is appearing more number of times, then it is more contrast. So how do you know how much is the brightness or contrast factor of an image? This is known from the histogram. Histogram is nothing but the graph, okay, which presents how many number of times each pixel has appeared in the image. So Matlab gives you a very easy function of calculating the histogram. You can calculate the histogram as now, because histogram is a graph which gives the total number of times 0 pixel has appeared, 1 pixel has appeared. Whenever you want to display the histogram, you cannot use IM show. you rather need to use plot command. Okay, plot is a command in Matlab to plot any graph. So if we look at this histogram, one thing is very much clear, that the color value between 50 to 100 is very high. So image is on the blackish side. So if you can increase the white pixels, okay, and if we can make this histogram more or less equivalent, if we increase this white pixel, it will be more balanced, okay, visibility will improve. So based on the histogram, okay, if the contrast is low, increase brightness. If the brightness is high, increase contrast. So this balancing is also known as histogram equalization. Okay, after you equalize the histogram, your histogram will be more or less flat histogram, such that wherever black pixels are more, it will be, I mean, their color value will be increased. Wherever white pixels are more, their value will be reduced. Okay, so histogram equalization can also be done histogram equalization can also be done by using a command which is called histeq. So im2 is equal to hist eq of im subplot 2 comma 2 comma 3 im show im2. This is equalized histogram, and subplot 2 comma 2 comma 4 im hist im2. So there is one thing with histogram. If you directly write im hist command and do not want to plot it, Matlab would automatically do it for you. Okay, you need not to take the histogram value and then plot it explicitly. If you call im hist, automatically it is going to calculate the histogram and plot it. So look very carefully here. This was my normal image. Okay, after histogram equalization, this becomes the image. So whichever are the objects, okay, of concern, you can see the objects are much more brighter, okay, and the color difference in correspondence to its neighbor has changed, such that the histogram is equalized. You can take other images and you can initiate, I mean, you can compare so we shall use the code from yesterday to analyze it. This will give a much better understanding. See, as far as the visual quality is concerned, the quality of this image is much better than the quality of this, because as we explained at the beginning, theoretically its brightness value is not changing significantly with respect to its background, and this image is also looking quite dull, okay, quite contrasted. As you can see, the values towards colors from 0 to 50 are quite high. So after histogram equalization, after balancing, white pixels have got more brighter, so the histogram is looking more balanced, the image quality improves. Okay, now the whenever we perform any image operation can be performed in two domains. Okay, one is known as the spatial domain, the other one is known as the frequency domain. Okay, the histogram equalization operation that you see, it's a spatial domain operation. Okay, spatial domain in the sense any operation which will be applied directly on the pixels in x and y direction. Okay, further image operations are divided into two types. Okay, first is a point operation, which are also called no memory operation. Okay, point operations are also known as no memory operations. There is a second type of operations which are known as neighborhood based operation, an operation where a pixel's modification will depend upon how its neighbors are. Okay, now what is a point operation? Yesterday we have seen one formula for converting red scale image into grayscale image, that is known as point formula. That is because for every pixel the formula will be calculated independently, will not be concerned of what is their value in the neighborhood. One of the example is say I am into 5. That means I am increasing the pixel values, okay, by multiplying it with 5. Okay, now there is a difference between histogram equalization. See the difference here. Okay, this is not really any balancing activity. What we are doing is all the pixels values, I am increasing it by the order of 5. Okay, so every pixel will get increased. The image will be looking more brighter. This is known as point operation. So each pixel will be multiplied by 5, no matter whatever its neighborhood pixels are. I am not concerned. Now, but most of the image operations, any meaningful image operations, would be depending upon the neighborhood. Say for instance, this is one typical image, okay, with 9 pixels. The center value is white, okay, and the corresponding values, all the neighborhood values are red. So you can easily say that the center value is noisy, right? If we compare it with respect to its neighborhood, the center value differs quite a great deal with its neighbor, right? So any kind of image operation on any pixels most of the time depends upon what are the neighbor values, and based on that only we can perform the operation. Now whenever we want to perform a neighborhood based value, the first thing that is important in image processing is to define frequency. Now in the case of one dimensional signal, defining frequency is quite easy. That is the amount of time after which a signal is going to be repeated. Okay, we tell that a frequency, a number of times a signal is repeated per second. Okay, that's known as the frequency. But how do you define frequency in the terms of images, in the terms of a two-dimensional signal? Because whichever operation we'll talk about, it's nothing but the filtering operation. Now any filtering, whether it is two-dimensional, three-dimensional, one-dimensional, will be of three major kinds: low pass filtering, high pass filtering and band pass filtering. In order to define what is low pass filtering, we should also know what is low frequency. In order to define band pass, we should know what is high frequency. So how do you define frequency in images? In signal it is fine, it's a sinusoidal signal. So the highest amplitude is appearing twice. Okay, so the frequency is 2 Hz. It's well defined. In the case of images, how you are going to define the frequency? See, listen very carefully, okay? How do you define frequency in the terms of images is number of pixels after which one color is repeated is called the frequency of that color. Alright? Number of pixels after which a color is repeated is called the frequency of that color. Okay? Now here we have two colors, white color and red color. Can you tell me which is low frequency, which is high frequency?
High frequency red and
No. High frequency is white, low frequency is red. Let me define once more. Number of pixels after which a color is repeated is known as the frequency. So how many pixels after which red is repeating? On an average, after every next pixel red is being repeated. But after how much white is repeated? White is never repeated. So conceptually its frequency is infinite. That means after infinite number of pixels it might get repeated. So obviously because infinity is much higher than that, so white pixel is known as the highest frequency. So any image will be comprising of high frequency and low frequency. Now when you analyze any image, in this section, okay, in this zoom section, can you tell me what exactly is the low frequency and what exactly is the high frequency? Carefully now. Aren't the black pixel comprising the edges of this images? These are edges, right? Would you agree? This is an edge part. This is an edge of the image. Edge is a section where both side color values will be different, okay, or which will drastically differ from the edge. This is an edge section. This is an edge section. This is an edge section, right? So an image essentially will be comprising of high frequency data and low frequency data, okay, low frequency color, and edges by default are high frequency, okay. Now if I want to separate the high and low frequency of the image, what exactly I have to do? Say, if I say that I want to implement a low pass filter such that I do not pass the high frequencies. So what I need to do? For low pass filtering of the images, you need to suppress these colors. Okay? I can easily suppress this color if I replace these colors by more of red colors. Here also there is a variation. Even though it looks a simple red, this is not a simple red color. There are variations in the pixels. If I can eliminate this variation, fill most of the images with reddish, I'll be easily able to suppress the high frequency data and will be replaced by those pixels which are repeating more number of time. So any image which loses its edge, that becomes blurred. Okay? Any image which when you take a photograph while moving vehicle, you'll see that you'll be able to see the blur images which you'll not be able to prominently determine which is the boundary of the objects, okay? So in image processing terms, we call blurring of the image is a low pass filtering, okay? Another very common low pass filtering method is a median filtering, where what you do is you select one neighbor, check the value of all its neighbors, calculate the median and then replace the center with that median value, okay? Now if you go by this, obviously because this is the same color, median of this one will be red. So when you filter, you can easily filter this with, say, this was the color. Filter this with red color. So when you do that, your high frequency pixel will go up. So if you select one pixel calculate its neighborhood, which are the pixel are there, then take mean or median, okay, of those pixels and replace the center pixel. Your high frequency data will go off. Okay. Let us see one of the examples of median filtering. So this is one of the methods of low pass filter. So what we do is, for any frequency filter, you need to generally define the image and also the neighborhood size. 5 cross 5 in the sense, how many pixels will take in the row wise, how many pixels will take in the column wise. Okay, so for each pixel 25, total 5 number of pixels in its neighborhood, in the rows and in the column, will be selected as the neighborhood. It will calculate the mean of all of them and then replace the center value with the mean. Okay, so let us say that this is median filter. Now there is one more thing. See, because we say that the image is comprising of both high pass filter and low pass filter, if we subtract, this is my original image, this is the low pass filter image. If I subtract this from this, what will be the result? So obviously any pixel when subtracted from the same pixel will result in 0. 0 is nothing but black color. Then white minus red. Okay, so white comprises of red, green and blue component. Okay, so if I subtract red, red equal to 0, green will be 255, blue will be 255. Okay, so this will be the result. But very interestingly, if you see, in this case, this is actually the edge pixel, isn't it? Because the color value in all its neighborhood is changed. Okay, so if I perform low pass filtering on the image and subtract that low pass filter from the original image, the resultant will be the edges of the image or high pass data. So if you can low pass filter any image and then subtract from the original image, you will automatically get the high pass value. So let us see this practically. IM5 equal to IM minus IM4. Are you able to see now? These are the edges in the rows image. This is the median filtered image, which will suppress the edges to a great deal. After suppressing the edge, when I subtract from the original image, it is going to get me the edges. Or if in case there is no edge, so let me also make one synthetic image on which we can understand this in a much better fashion. And let me apply this on the color image. We also know how to apply any algorithm which is made for grayscale image to color image. IMC. What is IMC? IMC is the color image. What is IMC? Okay, IMC is equal to IM. IMC is this image. So median filter to IMC colon comma 5. What is the problem it's giving? So this is the data that you get when you filter. Now if you reduce the amount of filtering that you need to perform here, say if you do 9 by 9 median filter, which means the effect of filtering would be much more higher. Can you see that the image is more blurred? The edges are no more prominent. If you look at this image and this image, this is more of a blurred image. Okay, the color variation here will be minimum. You can see this is more of a smooth image. So median filtering is also known as smoothing process. See the color variation. Color variation is very minimum. When you look at this, you can compare the color variation from one pixel to another pixel in both this one and corresponding to the median filtered output. Therefore, when the median filtered output or the smooth output is subtracted from the original image, you get the high pass data. There is one more method by means of which you can calculate the age. That is by calling age function. So IMAge is equal to age, and age function always take the grayscale images. Okay, so you need to always pass grayscale images over here. This is the edge image that you get by calling the edge function. But when you look at this two, there is a lot of difference between the edges that is returned by high pass filtering and the edges that is returned by Matlab function. Okay, so therefore I always prefer a high pass filtering based edge detection technique rather than Matlab filtering, because this gives much more prominent edges, okay, the edge that we'll be requiring. So this is it. Now yesterday we saw one kind of thresholding where we find out certain pixels, and then what we did was we altered those pixels. So say for instance IM is greater than 100. Okay. Now when you use certain expression like this, which means that whichever pixel in IM, okay, is greater than 100, that will be true. Rest of the all pixel will become false. Okay. So any notation which is of this kind, where you compare certain pixel values in the images and then assign that result into another image, this is also known as masking. Okay, it will result in a mask image where white pixel, it will have two values, ones and zeros. Such images are also known as binary image. White or one will be on those pixels where it meets the condition. In other pixels it is going to be zero. So this is also known as a binary image. The difference between this image and this image is there will be pixel values from 0 to 255, whereas here there will be only two pixel values, ones and zeros. Okay, when you look at the workspace, as you can see IMN, okay, or mask image is 207 into 244 logical. Its values will be varying from zeros and ones. So any logical image will also support all the logical operation like AND, OR, NOT. Okay. Say for instance, this is the mask image. Okay, I can perform the NOT operation. Tilt operation is the NOT operation in Matlab. The overall principle is, so this was the mask generated out of the thresholding. This part was black, this part was white. After performing a logical operation, that is after performing the NOT operation, whichever part that was white, black will become white, whichever part that was black will become the opposite. One of the advantage of generating the mask is that this becomes quite helpful in image segmentation. Okay, how? Now as you see that this is white and rest of the things are black. Okay, so black value is 0. But this image is a logical image. If I convert it into double type of image and if I multiply this original image, I'll be only able to retain this part of the image and rest all part will become 0, isn't it? When you multiply anything with ones and zeros, the pixel values where 1 is there, that will be retained. Wherever 0 is there, that will be left out. Let us see this. So, using mask for segmentation. As the mask image is logical, just convert it into double data type. Okay. Now, see, I applied one threshold. Okay, as per this threshold, those pixel values which were lesser than, which were greater than 80, they were made 1. Rest of the pixels were made 0. That resulted in a mask like this. Okay. Now I want to select only the pixels which are white over the mask. Okay. So what I do, I convert this into double data type because logical data type cannot be multiplied with. Okay, you can have only logical operation on logical data type, that is XOR, NOR, AND. So I convert it into double data type. Then I convert the image which is of uint 8 type also to double. Then each of the channel I multiply with the mask. So wherever mask is 0, original color value becomes 0. That becomes black pixel. Now you can have various something like this. Okay, so in this way you can eliminate the unnecessary part of the images, okay, by applying the threshold. So this is also known as threshold based segmentation. Okay, so histogram is a spatial operation, histogram equalization is a spatial operation, followed by the low pass filtering, which where either you can use median filter or averaging filter, or you can use Gaussian kernel. When you subtract a low pass filtered image from the original image, you basically get the edge images. Okay. Now you can put thresholding onto any image by taking any threshold condition and applying it over any other image. The resulting image for thresholding is a binary image, logical image, where 1 will be the pixels where this condition is true and 0 will be the pixels where this condition is not true. Once you have got a mask, you can apply the image operation only over the mask, segmenting out the unnecessary part of the pixels.